Alright, so if we go down to chapter 7 on our formula sheet, alright, so we're looking for the binomial probability distribution formula. So looking at this one right here. So remember, this is a combination here. This P, that was the probability of a success. And then 1 minus P, remember I told you some books they call that Q, but you just simply say 1 minus the probability of success, so that would be like the probability of failure. Alright, and then we have these powers here. X is the number of successes in N trials, so that power is X, and this power up here is N minus X. So really we have to work out this, and then multiply it times this, and that will give us the probability that we're looking for. Okay. So I'm going to pull up a homework type problem, and I'll work through it with you so that you can see how to work one of these. I know we may have briefly touched on this before, but you don't have to write down everything in this problem. I would probably just write down what we're trying to find here at the bottom. So it says, assume the random variable x has a binomial distribution with a given probability of obtaining a success. Find the following probability given the number of trials and the probability of obtaining a success. So here's what we're trying to figure out. The probability that x is greater than or equal to 4, if we know that we have 6 trials, that's the number of trials, and the probability of success is 0.5. Alright, so if we want to know the probability, this isn't just x is equal to 4, this is probability that x is greater than or equal to 4. So to do that, we're going to need to find the probability that x equals 4 plus the probability that x equals 5 plus the probability that x equals 6. So to work this one problem, we have to work out these 3 problems. Okay? And we use the same formula every time. We have our n, we have our x, we have our p. And so we can calculate 1 minus p, and we can calculate n minus x. So let's do each one of these separately. They're not going to take very long. We can even use technology to help us if we need to do the combination, because we can work it out probably a little faster than we can. But the probability that x equals 4 for this binomial probability distribution is going to be, so we're going to have 6c4, and then we're going to say that times, we were told the probability of a success is 0.5. So it's going to be 0.5 to the x power, and we know that x equals 4 for the first problem. Alright, and then we have 1 minus 0.5. What's 1 minus 0.5? Just 0.5, right? So it's going to be 0.5 to the n minus x power. So 6 minus 4 power, or second power. Okay. Now, if I work this out now and I write the answer down, I'm probably going to take it out several decimal places, because, you know, depending on how they want me to write my answer, usually we'll round to 2 or 3 places. So I'm going to take it out to 4 or 5 places. So the first thing we need to figure out is 6C4. Again, your calculators, even the little scientific calculators, will do that pretty fast. But that's 6 factorial divided by, what, 6 minus 4 factorial times 4 factorial. So what's that answer? What's 6C4? Everybody at once. So I had 6 factorial divided by 6 minus 4 is 2 factorial, and then divide by that by 4 factorial, 15. All right, times 0.5 to the 4th power all right, that's 0.0625 times 0.5 to the 2nd power is just 0.25. All right, so that's going to be the probability that x equals 4 in this problem. So 15 times 0.0625 times 0.25. All right, and I'm going to write that out all the way out, 0.234375. Plus, now I'm going to do the probability x equals 5. So it's just going to change just a little bit. My x, instead of 4, will be 5. So this will be 6C5 times 0.5 to the x power, so it's going to be to the 5th power, times 1 minus 0.5 is still 0.5 to the n minus x power. So 5 minus 4 power is the 1st power. Alright, 6C5 is 6 factorial divided by 1 factorial divided by 5 factorial. Wait, that was wrong. Can't be right. So 6 factorial. I say it can't be right. It could be right. So divided by 6 minus 5 is 1 factorial divided by 5 factorial. Okay, 6. I punched something in wrong. Okay. So, we got 6 times 0.5 to the 5th power, 0.03125, times 0.5 to the 1st power is 0.5. So let's type that in the calculator. It's going to say this times 6 times 0.5 at 0.09375. Plus, got 1 left, x equals 6. Alright, so this is 6C6 times 0.5 to the 6th power times 0.5 to the what? 0 power, right? N minus x is 0. Anything to the 0 power is 1. Okay? 6C6 is what? Just 1. So the only thing I have to do in the calculator is 0.5 raised to the 6th power. 0.015625. So if I add those three answers together, I'll have my answer. All right, so 0.34375. All right, it's not too bad. It's just all those small calculations that we have to do. All right, here's a word problem, one that we would have to figure out more of the stuff. And so you'll have something like this in your homework. You don't have to copy it down. Again, you'll see this again in your homework. The main thing I would copy down is when we figure out what exactly the problem is, when we apply the formula, or what we're trying to figure out, all the parts. But if you want to write it down, feel free. All right, a researcher wishes to conduct a study of the color preferences of new car buyers. Suppose that 40% of this population prefers the color blue. If 12 buyers are randomly selected, what is the probability that exactly 9 buyers would prefer blue? Okay, so let's write down everything that we know. So we were told that 12 buyers are randomly selected. So that's the number of trials, n equals 12. We were told that 40% of the population prefer the color blue for a car, I guess in this certain area. Who knows, maybe their school colors are blue, so they like blue, so they buy a lot of blue cars. I don't know. That just tells me that P, the probability of success, which in this case is that they have a blue car, is 0.4, right? 40% is 0.4 or 0.40. All right. Now, I want to know the probability that exactly 9 buyers would be selected out of the 12. So I want the probability that x equals 9. So it didn't say is greater than or equal to 9. It didn't say greater than 9. It said exactly 9. So when it says exactly, we just have to work out one problem. Okay? So let's apply our formula. It's NCX times p to the x times 1 minus p to the n minus x. All right, so I want to find 12 C9 times the probability of success was 0.4. So that's 0.4 to the x power, so to the 9th. And then what's 1 minus 0.4? 0.6. And that's to the n minus x. So n was 12, x was 9. 12 minus 9 is 3. So you check my math. 12C9 That would be 12 factorial divided by 3 factorial divided by 9 factorial. When you did that in your calculator, did you get 220? All right, I'll just assume I'm correct. Hopefully, yes. Times 0.4 raised to the 9th power. 0.002624144. It's important that we keep this exact as we can. Times 0.6 raised to the 3rd power. 0.216. All right. So we want to multiply those 3 together. All right. I'm going to take this out to 4. Let's see. I'll take it out to 4 significant digits. So 1, 2, 3, 4, or I'll round to 4 places. How about that? So that'll be 0.0125. So there doesn't seem like there's a very good chance that exactly 9 people would have a blue car. And of course, if we wanted to, you know, if this was real data, then we would probably figure it out for every number, and then we could figure out the probability that, you know, say 9 or more, or 9 or less. 9 or less would be a lot of work, right? Because we'd have to do 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so that would be one way. The other way would be to use the complement. So, for example, on this previous problem that I worked, right here, where I found the probability of x being greater than or equal to 4. If the problem would have been the probability that x is, let's say, less than 4, then that would have been the probability of that x equals 3 plus the probability that x equals 2 plus the probability that x equals 1 plus the probability that x equals 0. Another way to do that, though, is to say 1 minus the probability that x is greater than or equal to 4. That's using the complement. So I could take my answer down here that I get from greater than or equal to 4, which was only 3 calculations, and then say 1 minus that, and that would give me the probability that x is less than 4. Because remember what all the probabilities have to add up to. If I take every possible probability, if this is any kind of probability distribution, it always has to add up to be 1. So we can use the complement of the event sometimes to help us shorten our work, if that makes sense. If it doesn't, maybe after you work a couple, it'll make a little more sense. Let's see if I can find one where using the complement would be faster. Because sometimes that's what we want. We want to be able to find the answer as fast as possible, right? Alright, I found one. So this is a problem where using the complement, now do you have to use the complement? No. But using the complement will help you work the problem out faster. So I'm not going to worry about the word problem part. This is the problem that we're looking for, and you're given these values. So let's pretend that I didn't understand how to use the complement. Then, if I didn't understand how to use the complement, to find the probability that x is less than 3, I would have to say, okay, the probability that x, and you don't have to write this first part down, but you can, it may help you. That would be equal to the probability that x is equal to 2. I'm going to change one thing on this problem. Y'all bear with me for a second. I'm going to change this to the probability that x is less than, I'm going to change one thing. How about 4? I'm going to change that to a 4. So we'll change this to a 4. Alright, so if I wanted to know the probability that x is less than 4, and this is a binomial probability distribution problem, that would be the probability that x is equal to 3 plus the probability that x is equal to 2 plus the probability that x is equal to 1 plus the probability that x is equal to 0. Another way to think of this problem, though, is for me to figure out 1 minus the probability that x is greater than or equal to 4. Greater than or equal to is the opposite of less than. The way that I would figure that out is I would say 1 minus the probability that x is equal to 4 plus the probability that x is equal to 5. Since I only have 5 trials, I can't do any more. That's as far as I would go. Alright, so what would be easier? Using our formula 4 times and adding those together? Or using our formula twice and then subtracting that from 1? Of course, using it twice and subtracting it from 1 would be faster. Alright. Unfortunately, there's not just a couple buttons you can push in your calculator to do these. Now, your calculator does make it to where sometimes you can put a lot of these in at once, or you can do your combinations and your things raised to powers and just put them in, and you don't have to do each calculation separately like I'm doing. Alright. So here's how I would do this, though. First, I would work this out, and then I would work this out. So this would be, I had to look at my numbers here. This would be 5C4 times, the probability of my success is 0.7. So it's 0.7 to the x power times 1 minus 0.7, or 0.3, to the n minus x power. And n minus x here was 5 minus 4 would be 1. Then I'm going to add the probability of x equals 5. That's 5c5 times 0.7 to the 5th times 0.3 to the 0, because 5 minus 5 is 0. Alright, so I can do this one a little quicker. I'll just punch it all in my calculator. I don't have a easy way to do my combination, but if I understand what I'm doing, I can pretty much do this in my head, right? So this is going to be what? 5c4 is 5 factorial divided by 1 factorial divided by 4 factorial, or just 5. If you do in your calculator, you just get 5. So it's going to be 5 times 0.7 to the 4th power. 0.7 raised to the 4th power times 0.3 to the 1st power, or just 0.3. Alright, so that's 0.36015. Alright, so now I'm going to do the second part. 5c5. Well, that's just going to be 1. So that's 1 times 0.7 to the 5th power, and then 0.3 to the 0 power is 1. So I don't have to do anything there. So 0.16807. So I'm going to say 0.36015 plus 0.16807. So that's those two added together. And then I need to say 1 minus that. Alright. The tricky way to do that in a calculator is that I could just make that negative and add 1 to it. 0.47178. 0.47178. So sometimes using the complement will speed that up just a little bit. It's not too bad. And remember, if you forget your formulas, they're here on this formula sheet. Now, finding the expected value is really easy. Not sure if we went over these formulas, but they're so easy that I can go over them really fast. They're probably the easiest standard deviation and variance formulas that we'll cover. All right. If you know that you have a binomial probability distribution, then the mean, that's the expected value, is just equal to n times p. All right. So on any of those problems, if I wanted to know the mean on this previous problem, I would say n, that's 5 times p, 0.7. 5 times 0.7 is 3.5. That's the answer. Okay? If I want to find the variance, remember that if its population is sigma squared. It's equal to n times p times 1 minus p. That's it. So if I wanted to find the variance of this previous problem, it would be 5 times 0.7 times 0.3. 5 times 0.7 times 0.3. That's n times p times 1 minus p. You talk about easy. Now, is it easy to remember all these formulas? No, it's not. So that's why I let you use a formula sheet. Now, how do you think you find the standard deviation? You just take the square root of that. So the standard deviation, that's just sigma. That's the square root of n times p times 1 minus p. Or if I wanted to do that up here, it will be the square root of 1.05. Do that in a calculator. So I'll just say 1.025. It just depends on how many decimal places that your homework asks for. So finally, a standard deviation and a variance is easy to find. All right, that's the first one. So I need to put a lot of those on the test, right? All right. So moving along. All right, the main topic of this chapter that we're going over is all about discrete probability distributions. Okay, discrete probability distributions. This was the binomial distribution. Next, we're going to talk about the Poisson distribution. All right. So we are going to have to use a function in the calculator that you may or may not have ever used much in your life. We do have to use our exponential function. I know if you've taken college algebra that you understand what the exponential function is, e to the x. So we are going to have to use that button in our calculator. All right. So we'll practice a little bit with that. So what is a Poisson distribution? Well, just like with the binomial distribution, we have certain properties or conditions that your distribution must follow. Okay? In some ways, it is similar to the binomial distribution. You must have a number of random variables that you can count. and there has to be a total number of successes, just like with the binomial distribution. So if you look in the PowerPoint on this section, you'll see successes occur one at a time. So, you know, just like if we were rolling a die, we could roll a die as many times as we want, but we can't roll a die once and get a 5 twice, right? You can only get a 5 once every time, or a 6 once every time, or a number once every time. So you do have successes that occur one at a time. All right, the main difference, the main difference is we're going to be looking at situations where we don't have a countable total number of successes, because we're going to be looking at things like time. So occurrences of a success in any interval is independent of the occurrence of a success in any other interval, is what the way that your textbook puts this. But you can just say the Poisson does not have a fixed number of trials. So the way that your PowerPoint points that, it says the occurrence of a success in any time interval is independent of the occurrence of a success in any other time interval. So let me explain to you the situations we're going to be looking at here. So let's say that, let's just say that I wanted to figure out the probability that Zaxby's served 120 people within a 1 hour period. Okay? Well, I could then maybe look at the probability that it served 125, or the probability that it observed 75, or the probability that it observed 2,000 in 1 hour. Now, is that going to happen? Probably not. But the probability that it served 200 in 1 hour, that's probably a pretty good chance. But what do you think the probability that that particular restaurant served 15 million people in 1 hour? I mean, that's not going to happen. It's unlikely, right? I mean, how could that even happen? But there's not a fixed number of trials. Okay? So that's the big thing. Even though there's not a fixed number of trials, there gets to a point where it would just be so crazy that it wouldn't make any sense. Like if you just try to put it in a real world situation. So the Poisson distribution, it uses a fixed interval of time in which the successes are recorded. All right, and again, if I wanted to know the probability that within 1 hour I could flip a coin and get 250 heads, that might happen if I flip fast enough in an hour. But the probability that I can flip a coin for 1 hour and get 5 million heads, that's not going to be very, it's not going to happen. But I could still try to figure it out. it would just be a probability that would be super close to 0, so close that it would probably be 0. Okay? So that's the biggest deal. So there's not any limit, theoretically, there's not any limit on the number of trials, but a large number of trials is not very likely. All right. So I'm going to write down the formula. Don't want you to freak out on me or anything. It's just a little different variables, but it's not too bad. All right, so the probability that we get some fixed value of x, some x out of some total number of trials, is equal to e to the negative lambda power, just another variable. It's kind of like an upside down y. It's lambda. All right, times lambda to the x power divided by x factorial. Now remember, the number of trials, that x can be, it could be none, it could be 1, it could be 2, it could be 3, and it could go on forever. But large numbers of x are probably not going to happen unless it's a large amount of time that we're looking at. So what is e? Well, we know from algebra that e is a transcendental number. It's kind of like pi. It's a symbol that stands for a number that occurs a lot in nature. All right? And it is approximately 2.71828, and it just keeps going on and doesn't create a pattern. If you ever want to carry it out to more digits, and we're going to use the calculator to carry out more digits for us, but we never want to just plug in a rounded value of e. But if we wanted to find out e to a couple more places, we could just say e to the first power, and you can see it's kind of like pi. It just keeps going on forever, and it happens a lot in nature and in mathematics, in physics. Okay. All right. Lambda, the upside down y I was telling you about, that is the mean number of successes. If you're wondering how I'm saying this word, that's L-A-M-B-D-A. There is an uppercase and a lowercase, so this isn't the one you're used to. It's probably because this is, I believe this is the lowercase lambda. One fun fact about lambda or about Poisson distributions is that the mean equals lambda and the variance equals lambda. There is a function in the TI calculators for the Poisson distributions. The way that you have to put it in, though, is a little different. There is a technology section in your book, in this section, that shows you exactly how to enter it in. This is one, though, to me that's not too bad, so I usually don't even use technology to do this, even though the variables look a little different. There's a way to do it in Excel. There's a way to do it in the TI calculators, but again, I usually don't do that very often. So as your X values get larger, sometimes your probability ramps up and then goes back down. Sometimes your probability starts high and then goes down. There are a couple of examples of what the Poisson distribution would look like with different values of lambda. I'll show you a couple of those real quick. So here is what the distribution would look like graphed if lambda was 0.3. Even though you can't tell, these are values here. This is so, when you get to 5, it's so close to 0, even though it says 0, 0, you could carry it on out and it would eventually be a number. But it's so close to 0 that it's practically 0. But as the values of lambda change, of course, the distribution is going to look a little different. So here's another Poisson distribution where lambda is equal to 3. Remember, lambda is a mean. So, you know, of course, we're going to have to know what x we're looking at, and then as lambda equals 3, you can see it goes up, and then it goes back down. So you can tell that looks a little more bell-shaped, but it has a little skewness there. It is skewed a little bit. Which way? To the right? To the left? It's one or the other. Now, as lambda gets larger, check out what happens. Here's where lambda is 12. So as lambda becomes very large, you can see that we do start to have a bell-shaped distribution, or a normal distribution, which may not mean much now, but eventually it will mean a little more. All right, so let's look at an example of how we could use a Poisson distribution to figure out a probability. It's actually kind of neat because it's the kind of problems that if you were owning a business and you could figure out maybe the mean number of items that you're going to sell at your business, then you could figure out the probability that, say, you're going to sell 10 items an hour or 20 items an hour. Of course, you would need to have data built up over time that you could use. All right, so here is a very good example. This is something that has affected, I'm sure, all of us at one time or another. How frustrating is it to go to the bank and need some money, and of course you're going to go through the ATM because you don't want to go in the bank, and then the line is out to the road. If you go to, I know a particular bank in town that doesn't have a lot of access to its bank. There's only one of those. And many times I've tried to go to the ATM and the line be out to the road and I really have nowhere to go, so I have to make another loop and hope that, you know, it speeds up a little bit. So here's a problem about a bank automatic teller machine. I really wish that there was an easier way to get money out, but I guess if it was too easy, then people would just steal it. So, suppose a bank has one automatic teller machine. Customers arrive at the machine at a rate of 20 per hour, according to a Poisson pattern. All right. So here's what we're going to do. First, we're going to figure out what is the probability that no one will arrive in a 15-minute interval. All right, so X is going to be equal to, if no one arrives, what will X be equal to? 0. Okay. So it's going to be the number of people that arrive in the 15-minute period or interval. Now, we know that on average, 20 arrive per hour. So, on average, how many arrive in that same period of time, this 15-minute interval? We're going to have to use some common sense. So, if on average 20 people arrive in an hour, how many 15-minute intervals are in an hour? 4. So does that mean 60 people arrive every 15 minutes? No, that wouldn't make sense, would it? So you have to divide by 4. So if we know 20 arrive in an hour, then on average, 5 will arrive every 15 minutes. So my lambda is 5. Okay, so let's use our formula and figure out the probability. So the probability that 0 people will arrive in a 15-minute interval, if normally on average 20 arrive per hour, that's going to be, let's use our formula, e to the negative alpha, so it's negative 5 times alpha, what was that? Not alpha, I meant lambda. Where is alpha coming from? Lambda. So it's e to the negative 5 times lambda, which is 5, to what power? The 0, because we let x equal 0. And that's divided by 0 factorial. Remember, 0 factorial in mathematics is defined as 1. So that's okay. It's not dividing by 0. So 5 to the 0 power is what? 1. So all we have to do is type in e to the negative 5, and that will give us our probability. So I think in the most scientific calculators, you have to push in the e first, and then it'll just put your parentheses there. In this, I have to put in 5 negative, and then push my e button. So 0.00674. I'll round to 3 places. 0. Is that a very good chance? That's 0.7. I'm sorry. Yep. 0.674. That's not even a 1% chance that's going to happen. All right? So a very, very small chance that would happen. What do you think the probability that Zaxby's is going to serve 0 people in a 15-minute interval is? Probably a lot less than that. Because I would hate to know on average how many people they serve in an hour. And I'm just using that example because that's a new restaurant or a new fast food place in Brookhaven. All right. So now, What is, let's see, here's another problem. Same situation. What is the probability that in a 15-minute period at least 3 people will use the machine? Now there's one problem, there's one I guess problem with the problem, if that makes sense. Because we're not limited with the number of people that could come to the machine. Now, realistically we are. You know, in a 15-minute period, 5,000 people can't use the automated teller machine, right? But at least 3 would mean the probability that x is greater than or equal to 3. So that could mean the probability that x equals 3 plus the probability that x equals 4 plus the probability that x equals 5. Do you see where this is going and not going to work? Because that would just go on and on forever. But we can't work a problem to go on and on forever. All right? Now, what we can do, though, is we can use the what? Yeah, we can use the complement, can't we? We can say that the probability that x is greater than or equal to 3 is equal to the probability that x is, what's the opposite of greater than or equal to? Less than 3. Or actually, we have to say not just that, but 1 minus the probability that x is less than 3. Now, less than 3 there is another way to write less than 3, isn't there? Another way would be to write x is less than or equal to 2. I don't care which way you write it. It's just that if you write it this way, less than 3, you might would be tempted to work out 3. But you don't work out the probability for 3. Okay? Less than or equal to 2 and less than 3, since all of these are whole number occurrences, they mean the same thing. Okay? So here's what we're going to do. We're going to say 1 minus the probability that x is equal to 2 plus the probability that x is equal to 1 plus the probability that x is equal to what? 0. Guess what? We already have that last part worked out. We did that one already. We have it right up there in part A. So we won't have to work it again. All right. So we want to find the probability that x is equal to 2. We're going to use our same formula. All right, so you remember our formula. Oh, I've got it here somewhere. And I'll copy it down just again so we can just look at it and it won't look so crazy. So there's our formula. All right, so we're going to have 1 minus, and then we're going to work it out for 2. It's the same 15-minute interval. So it's going to be e to the negative 2 times what? Is that right? No. What's lambda? What did we figure out the mean was? 5. So it's e to the negative 5 times 5 to the what? 2 over what? 2 factorial. So that's our first part. And then plus e to the negative 5 times 5 to the 1, or first power, divided by 1 factorial. And we've already worked out this third part, but I'm going to write it down anyway. E to the negative 5 times 5 to the 0 divided by 0 factorial. Alright, so let's type this in the calculator. And I'm going to carry each one out to about 5 decimal places. Alright, so here's e to the negative 5th power. I got to say that times 5 squared is 25, divided by 2 factorial is 1. So there's the probability that exactly 2. And I said I was going to round it to about 5 places. So 0.08422. And then we're going to do the same thing for the probability of 1. So that's e to the negative 5th power times 5 to the first divided by 1. That's 0.033. If I round that to 5 places, that's going to be 0.03369. Plus, and we figured out the other one, no use in doing it again, 0.00674. Alright, so I need to add those 3 together and subtract them from 1. Alright, so I'm going to say 1 minus that. So the way I can do that is just make it negative and add 1 to it. So, of course, this is a rounded answer, rounded to 5 places, but it's 0.87535. So what does this actually mean? That's the main thing, is that we understand what we're doing and what it actually means. So I don't care, I just want the answer. Well, makes a little more sense if we can think about it in a real world situation. Alright, so the problem was, what is the probability that in a 15-minute period more than at least 3 people will use the automated teller machines? That's 3, 4, 5, 6, 7, on and on forever. It's within a 15-minute period or interval, and we know that on average 20 people use this thing every hour. 5 use it every 15 minutes. So the probability that at least 3 use it is 0.87535, or about 87.5% chance that at least 3 people will use the teller machine within a 15-minute period. And it should make sense too. If 20 people use it per hour, or about 5 every 15 minutes, then the probability that at least 3 people are going to use it within 15 minutes should be pretty good. Pretty good chance. Well, about 88%, that's a pretty good chance. If it was an 88% chance of raining tomorrow, I'd probably wear a raincoat, right? May not happen, but it's a pretty good chance. All right, let's see if we can read through one more problem. We may not have time to do every calculation, but I do want you to be able to figure out like the mean or the lambda for the problem, because sometimes it's a little bit different. Like that one, we were given the mean for an hour was 20 people using it, and we had to use 15. Right? Or we were looking at 15 minutes, so we had to say 20 divided by 4 and get 5. Let's look at this problem. You don't have to write this one down. Let's just look at it and see if we can figure out what our variables would be. All right. So it says this telephone company considered buying a optical cable. So it wants to buy some optical cable from Optica Incorporated. So it says it wishes to replace approximately 100,000 feet of conventional cable with optical fiber. Since optical fiber is very difficult to repair, it is important that the number of optical cable defects are minimized. I mean, that makes sense. If you want to repair something, whatever you're repairing it with, you want to make sure that it's good material. All right, so it says Optica claims that on average there is 1 defect per 200,000 feet of cable. What is the probability that the replaced cable will contain no defects? Okay. So if it tells us that it's going to replace 100,000, then on average, how many defects would that be per 100,000 feet? If you have 1 per 200,000, how many is that per 100,000? That's right, it's just half, right? It's 0.5. So the mean for 200,000 is 1. So that means the mean for, it will be 100,000 divided by 200,000, or just 0.5. All right, there are tables then we could use to figure out the probability of replacing the cable with no defects. What would our X be right here if we didn't want to use a table? The reason why it would be hard to do this is probably because of the, let's see, we want the number of defects to be 0. Right? So, right, and then what we want, no defects. So what would that be? If I plug those in my formula. E to the negative, I may say alpha, I mean lambda. Sorry, so lambda, that's 0.5 times what? Lambda to the x power divided by x factorial. So that's what I need to plug in my calculator. That's 1, that's 1, so that's e to the negative 0.5 power. 0.5 negative e to that power. Round this to 5 places, 0.60653. So it's about a 60.6% chance, about a 60% chance that there will be no defects in the cable once it's put down. All right.